Hi, in this video we are going to talk about splay trees, so let's get started. Basically, what is a splay tree? It is a type of a binary search tree, so every node can have a left child and a right child, and basically the left child is smaller than the parent, the right child is greater than the parent. So all of the features that we have been talking about when we were discussing binary search trees is going to be true for splay trees as well. So most of the operations have ordo, log, and so logarithmic time complexity, but some operations are very slow. Unlike AVL trees, it is not a strictly balanced data structure, so splay trees are not as balanced as AVL trees, but basically that's why it's going to be faster, because it's going to take a lot of time for AVL trees to make it as balanced as possible on every insertion. Here, we are not going to make it strictly balanced, so that's why we don't have to bother about making it perfectly balanced, and that's why it's going to be faster. It is quite easy to implement it, and basically this is the most popular data structure in the industry. Okay, then you may pose the question that why is it good to use splay trees? Because there is fast access to elements accessed recently. So basically it is like a cache. So most of the applications of splay trees are related to caches, how we are able to retrieve data that we have used in the not too distant past. Okay, so splay trees are kept balanced with the help of rotations, and these rotations are exactly the same as we have seen for red-black trees or AVL trees. So we can rotate a subtree to the right and we can rotate a subtree to the left. For example, we have this subtree on the left with the root node D. It has a left child B and a right child E, and node B has a left child A and a right child C. So whenever we rotate to the right, the topology of the tree is going to be changed. So after rotating to the right, then the D is not going to be the root node anymore. It's going to be the right child of B. So basically we just rotate it to the right. So the left child of D in the original subtree is going to be the root node. So that's why B is going to be the root node. And as you can see, all of the features of the tree is going to be maintained in the sense that, for example, the in-order traversal is the same. What's the in-order traversal before the rotation? It is A, B, C, D, and E. What's the in-order traversal after the rotation? It is A, B, C, D, and E. So basically, they are the same. So that's why it is very, very handy to use rotations, because we just have to update the references. So basically, it is quite fast. And on the other hand, it's not going to change any property of the tree. For example, the minimum item, the maximum item, and the in-order traversal. So we just have to update the references and we don't have to bother about anything else. Okay. So what about the find operation for the splay tree? We have been discussing that the splay tree basically is a binary search tree. So we have to do everything like we do for binary search trees. But we make rotations when we find a given element we are looking for, and it is going to be the root node, and basically this is called displaying, when we make the node we are looking for to be the root node. So it's very, very important to see that in this case we are not going to make the rotations in order to make the tree as balanced as possible. We are going to make the rotations in order to make sure that the item we are looking for is going to be the root node in the next time. This is a very, very important fact. So for AVL trees and red-black trees, we have used rotations to make the tree balanced. In this case, we are not going to make it balanced. We make sure that the given item is going to be the root node. And basically with the help of these rotations, we are able to make sure that a given node, a given item, is going to be the root node. Why is it good? Because in the next search, it can be accessed very fast in ordo 1 constant time complexity. Why? Because after the rotations, the given node is going to be the root node, and we start searching for the items at the root node. So we just check whether, okay, this is the item we are looking for, yes, because with the help of the rotations, we have made sure that the item is going to be the root node, so we are able to access it order 1 constant time complexity. There are 3 ways we can make it happen: the zigzag situation, the zigzag situation, and the so-called zig situation. What is the zigzag situation? When the given node X we are looking for is a right child of a left child, or a given node X is a left child of a right child. It's very important that basically a tree-like structure, whether it's an AVL tree, a red-black tree, a binary search tree, is very symmetric. And this symmetry is the same for splay trees. It can be a right child of a left child, but it can be a left child of a right child. We have to make the same rotations. Okay, we are going to talk about the right child of a left child situation, but we have to do the same, exactly the same, in the opposite, so the left child of a right child situation. Okay, so we have the root node, the Y. We have a left child of Y, it is the Z, and the right child of Z is the X, the node we are looking for. So, in this case, the X is a right child of a left child, because it is the right child of Z, but the Z is the left child of Y. So we have to rotate node X to the left first. What does it mean? That basically we are going to end up a situation like this. We have the Y, and the left child of Y is the X, and the left child of X is going to be the Z this time. But it's still not good. Why? I don't want to repeat myself over and over again, but why are we rotating? Because we want to make sure that after the rotations, this given X is going to be the root node. This X is the node we are looking for. For example, we would like to find 23 in a search tree. And then after finding it, we want to make sure that it's going to be the root node. We can do it with the help of rotations. Why is it good? Because if 23 is the root node, then next time we are looking for it, it's going to be the first item we have considered. If it's the first item we consider, it's going to take order 1 time complexity to find it, going to be very fast, and this is exactly how caches are working. Okay, so of course it's not good because X is not the root node yet, so we have to make a right rotation. Okay, and basically in this case this node X is going to be the root node. I don't want to repeat myself over and over again, but it's very important to see that in this case the reason why we rotate is to make sure that this given node is going to be the root node, not to make the tree as balanced as possible. We don't care about whether the tree is balanced or not. Okay, what about the zigzag situation? There is a given node X. The node we are looking for, this node X, is left child of a left child, or a right child of a right child. It is very symmetric. Okay, for example this, because X is the left child of Z, and Z is the left child of Y. So this is the zigzag situation. So we have to rotate the node Z to the right. It's very important that we do not start with the node X. We start with the parent of node X, which is the Z. Okay, then we are going to end up with this situation. The node X is still not the root node, so we have to make another rotation. Okay, so we have to rotate node X to the right. And as you can see, this is the situation we are going to end up with. You may pose the question that, okay, this is not a balanced tree. Of course, it is not a balanced tree, but this is not the aim of a splay tree. For splay trees, we want to make sure that the node we are looking for, in this case the X, is going to be the root node. Okay, it's not going to be balanced, we don't care about it, because we would like to implement caches. So we would like to find the recently visited nodes, items, custom objects more quickly. And basically, if we rotate them to the top of the tree, it's going to be faster. Okay, then we have the last situation, the zig situation. We have to repeat the previous two steps over and over again until we get to the root node. But sometimes we end up at the left or the right child of the root, so we just have to make a single right or left rotations accordingly. In the previous situations for the zigzag situation and the zigzag situations, we had to make 2 rotations. Now, for the zig situation, we are not able to solve it with the help of 2 rotations because we just have to make a single rotation. So here the x is just the child of the root, so we have to make a single rotation. For example, this one, x is the left child of the root, so we just have to make a right rotation. And after the rotation, x is going to be the root node. Again, the aim of splaying is not to make the tree balanced. The aim of splaying is to make sure that the given node we are looking for is going to be the root node. Okay. Or for example, because it is symmetric, so this x can be the right child of the root node, we just have to make a left rotation. And we are going to end up with a subtree on the right. Okay, so just to summarize again. What is a splay tree? A splay tree is a binary search tree, so all the properties, as we have discussed for binary search trees, are going to be true. The left child is smaller, the right child is greater. The in-order traversal is the same. Finding the minimum and the maximum item is the same, so the leftmost item is the smallest one, the rightmost item is the greatest one in the given tree. So all of these properties are the same. But after every insertion, we are going to make sure with the help of rotations that this given item we are looking for is going to be the root node. So we have to make the rotations. But it's very important to know that in this case, we are not going to make the rotations in order to make the tree balanced. We are going to make the rotations to make sure that the given node is going to be the root node. There are 3 situations: the zigzag situation, the zigzag situation, and the zig situation. Basically, all of these situations are dealing with how to make the rotations. Why are we making the rotations? To be able to make sure that the given node is going to be the root node. Because if the node is the root node, then the recently searched items is going to be near the root, so on the upper region of the tree. Why is it good? Because it's going to take approximately constant type complexity to find the items we have been looking for in the not too distant past. And yeah, this is exactly how caches are working. So the most important applications for splay trees are caching. Thanks for watching.